Hello class, this is section 2.2, frequency distributions and their graphs. I'm your instructor William Buellman, and as always this is Stat 1200. So let's go over our objectives for this section. To be able to construct frequency distributions for quantitative data, to construct histograms, and determine the shape of a distribution from a histogram. So as always, we have a few definitions to get us started. First, for quantitative data, there is no natural categories. Therefore, we divide the data into classes. The classes are intervals of equal width that cover all the values that are observed. The relative frequency of a class is given by same way as we found relative frequency before. It's going to be frequency over sum of frequencies. The lower class limit of a class is the smallest value. So the lower class limit is the smallest value that can appear in this class. Similarly, the upper class limit is the largest value that can appear in the class. And then finally, we have the class width. So most of the time people think the class width is the upper limit minus the lower limit, but you have to be careful, it is not. It is the difference, so subtraction, but between two lower class limits, not the upper minus the lower, so be sure to remember that. So here we have example 1. The table below shows a frequency distribution for particulate data. So we have our classes on the left, and our frequencies on the right. So we're going to list the lower class limits for the particulate data. So they were 0.00, 1.00, 2.00, 3.00, 4.00, 5.00, and 6.00. Our upper class limits were what were the highest values that could happen in each class, which were 0.99, 1.99, 2.99, 3.99, 4.99, 5.99, and 6.99. So class width. Remember that the class width uses two consecutive lower limits. So we're going to go the lower for the second class minus the lower for the first class. So we see that the lower for the second class was 1.00 and the lower for the first class was 0.00. So therefore the class width is 1. So we have some requirements for choosing classes. When constructing a frequency distribution, there's no right way to choose the classes. However, there are some best practices. So here are the requirements that must be satisfied. Every observation needs to go somewhere. So every observation needs to be in a class. The classes cannot overlap. So that's why you noticed before we didn't have 1 to 2, 2 to 3. We had 1 to 1.99, 2 to 2.99. So there can be no value that can be in more than one class. The classes must be of equal width. So again, whatever the width of the class is, it has to be the same. It cannot change. there has to be no gaps, and even if there are no observations in that class, we still need to include it. So if we had 1 to 1.99 had some observations, and then 2 to 2.99 didn't have any observations, we still have to write the class 2 to 2.99, and its frequency would be 0. Here is the procedure for constructing a frequency distribution for quantitative data. So first, we have to choose the class width. Then we choose a lower class limit for the first class. This should be a convenient number that is slightly less than the minimum data value. So let's say you have data values from 12 to like 98. Maybe we'll, instead of choosing 12, we'll choose 10 because that's a nice round number. So then we have to compute the lower class limit for the second class by adding the class width to the lower limit for the first class. So the lower limit for the second class is equal to the lower limit of the first class plus the class width. So the fourth thing we have to do is compute the lower limits for each of the remaining classes. So we'll rinse and repeat what we did in step 3. We'll take it for the third class and we'll do the second class plus the class width. For the fourth class, it's the third class plus the class width. So we just keep doing that until we get to the largest value in the data set to make sure we've covered everything. And then you just fill up the table. You count the observations for each class and you make a frequency distribution. Computing a class width with a given number of classes. So sometimes we begin by choosing approximately the number of classes we want instead, and we don't choose the class width. We go, I want to have X number of classes, let's say 7 classes. What does my class width need to be? So first we need to decide that, or it'll be given to you by me. The way we compute the class width, once we know how many classes we want, the class width is equal to the largest data value minus the smallest data value divided by our number of classes. So that'll get us some number. Once we have that number, it's probably not going to be a whole number. It might be an ugly number. So what we're going to want to do is we're going to want to round that value to something convenient that makes it easier to work with. We'll see that in an example coming up. Example 2. The following table presents the number of hours a sample of 40 subscribers listen to Pandora in a given week. So we can see all the data here. So construct a frequency distribution with approximately 11 classes. So you've been given the number of classes to use, which is 11. And I also want you to do the same thing with the relative frequency, also using 11 classes. So first thing we need to do is to figure out what the class width is. So remember, the class width is going to be equal to the largest value, which was 52, minus the smallest value, which was 2, divided by the number of classes I want, which is 11. Which, if we do this, we get that this is approximately 4.545. Not very convenient of a number to work with, so I'm going to round it up to 5 and use a class width of 5. Much more convenient. So now we have our class width. So now that we have our class width, we can construct a frequency distribution. So we know the smallest value in the data set was 2, but that's not very convenient. So I'm just going to go ahead and start at 0. And remember, our class width is 5, so the next value is going to be 5, and 10, and 15, 20, 25, 30, 35, 40, 45, and 50, and we have to make sure nothing gets left out. But every hours, they were whole numbers. So this first class is going to be 0 to 4, the second one's going to be 5 to 9, and we will continue on with the same pattern. So now we have all of our classes figured out. So if we count the number of hours between 0 and 4, that happened 5 times. 5 to 9 happened 6 times. 10 to 14, 8 times. 15 to 19 was 9 times. 20 to 24 was 6 times. 25 to 29 was 2 times. There were no people who listened from 30 to 34 hours, but we have to include that class even though there's 0 in there. We still have to include it. From 35 to 39 there were 3. From 40 to 44 there were 0. From 45 to 49 there was 0. And there was 1 from 50 to 54. So now we have a frequency distribution with 11 classes that covers all of our data values. Alright, so here was the second part where we had to create a relative frequency distribution for those same classes. I've already written the classes here, so we're just going to start with the relative frequency. So for the first one, it was 5 times out of a total of 40 observations, which is equal to 0.125. The second one was 6 out of 40 observations. Then we had 8 out of 40, 9 out of 40, and I'm just going to finish the rest of this table, and then I will show you the answers in a moment. Here we are. Now we have all of the relative frequencies filled in. We have all the fractions and all the decimal values. Again, I always write it as fractions first because it's easy to just put frequency over total, and then I convert it to a decimal after the fact because that'll be easier to work with when we need to make graphs. So here is some practice for you. The Old Faithful Geyser in Yellowstone National Park alternates between periods of eruptions, which usually last from 1.5 to 4 minutes, with periods of dormancy, which are considerably longer. The following table presents the duration in minutes of 60 dormancy periods that occurred in a recent year. So what I want you to do is to construct a frequency distribution using a class width of 10, so I'm giving you the class width that I want, and using 50 as the lower class limit for the first class. So your class width is 10, and your first class is going to have a lower limit of 50. Your job is going to be to fill in the rest of the table and fill in the frequencies. So this is what you have. So go ahead and fill in this table and fill in all the frequencies. Answers will be in 3, 2, 1. Alright, so here are the answers we get. So my first class is from 50 to 59, because remember my class width is 10. So if I take 50 and I add 10 to it, that's going to be my second lower class limit, which is 60. So you have to remember, don't do 50 to 60. It's 50 to 59, and my next one is 60, and those are all my frequencies. So now we have histograms. Once we have a frequency distribution or a relative frequency distribution, we can put that in a graphical form by constructing what we call a histogram. Histograms are based off of frequency distributions are called frequency histograms. And based off of relative frequency distributions are called, shockingly, relative frequency histograms. Histograms are related to bar charts and are appropriate for quantitative data. A histogram is constructed by drawing a rectangle for each class. The heights of the rectangles are equal to the frequencies or relative frequencies, and the widths are equal to the class width. So far everything's been the same as a bar chart, but here's where it's different. The left edge of each rectangle corresponds to the lower class limit, and the right edge touches the left edge of the next rectangle. So essentially what that's saying is there's no spaces between the bars. So in a bar chart there were spaces. In a histogram there are not. They're all squished together, and we will see that coming up. So we're going to construct a histogram for the particulate data in example 1. So I will show you what that histogram looks like. Okay, so here I have everything set up for us. So now we're going to draw the histogram. So the first class went from 0 to 0.99, but the left edge is going to be 1, so that's why it's labeled 1 for the second class. So our frequency was 9. So you see how we butted up right next to 1. And then for the second class, from 1 to 1.99 was 26. So you're going to see we're going to start from 1, go up here, and it's going to touch 2. So you notice there's no space in between them. Now the next one had a frequency of 11. So again, there's no space. Then 13. Then we had 3. 1, and then 2. So we can see here, it looks a lot like a bar chart. We just smushed it all together. So here's some practice for you. You're going to construct a histogram for the Old Faithful data. Again, it's going to be frequency. And then you're going to construct a histogram for the Pandora data in example 2. Also, again, using frequency. So go ahead and do those right now. Pause the video, and then the answers will be coming in 3, 2, 1. Alright, so here's our 2 histograms. Hopefully this is what you got. So you notice the Old Faithful data. Here's the histogram for it up top. And then on the bottom we have the histogram for the Pandora data. And you'll notice there are some spots where there is no bars, but that's because there was no frequency there. So we don't omit those sections. We have to still include them. You don't just smush it together and act like they don't exist. If there's nothing there, if it's not at the front or at the back of the data set, we have to do this. So here we're going to talk about histogram shapes. So histograms have a few different shapes. The purpose of a histogram shape is to give a visual interpretation of the shape of the data set. So statisticians have developed terminology to describe some of the commonly observed shape. A histogram is symmetric if its right half is a mirror image of its left half. So if the right side and the left side look about the same, they're symmetric. Very few histograms are perfectly symmetric, but many are approximately symmetric. So a perfectly symmetric histogram would mean the left half and the right half are exactly the same. That doesn't happen very often, but if it's pretty close, we call it approximately symmetric. But what if they aren't? So a histogram is skewed if one side or a tail is longer than the other. So a histogram with a long right-hand tail is said to be skewed to the right, or also known as positively skewed. But it's less common. Normally we just talk about skew as in skewed to the right. Or if it's pointed to the left, the tail, it would be skewed to the left. Or negatively skewed. But again, we don't typically say positively skewed and negatively skewed. It's a lot more common that we say it's either skewed to the right or skewed to the left. So here we have an example of a few different histograms. A, B, and C. So if we look at the first histogram, we go, okay, what's the shape of it? So where's the bulk of the data and where's it tail off to? So if I look, okay, it's kind of tails off in that direction. So it seems like it goes off in that direction. So we'll call this. So again, it tails off to the left, so it's skewed to the left. So if we look at this histogram B in the middle, if I were to split this down the middle, that side and that side look pretty close. Is it perfect? Maybe not, but it's pretty close in shape. So I'm going to say approximately symmetric. And then finally we have C. So again, we look and we go, it looks like it goes off to the right. The data just goes on to the right. So this histogram is skewed to the right. So here's some practice for you. I want you to classify these histograms as either skewed to the left, skewed to the right, or approximately symmetric. So go ahead, pause the video, take a minute, and do that now. Answers will be shown in 3, 2, 1. Okay, so here are the answers. So we noticed the first one, the bulk of the data is on the left-hand side and it kind of goes off to the right. So again, skewed to the right. We look at the second one, we see the bulk of the data is on the right-hand side and kind of trails off to the left. So that one is skewed to the left. If we look at the third one, we see most of the data is in the middle and it kind of goes off to the left and the right about the same. So that is approximately symmetric. So hopefully you got those answers. So the final thing we're going to cover is mode. A peak or high point in a histogram is referred to as the mode. A histogram is unimodal if it has only one mode. Uni meaning one, so unimodal is one mode. And it is bimodal if it has two modes. In principle, a histogram can have more than two modes, but it typically doesn't happen very often, so we won't talk about it in this class anymore. Either histograms are going to be unimodal or bimodal that you see in this class. So here we have some practice. We're going to classify each one of these histograms as either unimodal or bimodal. So if we look at this first one, we see there's only really one bump in the data, so it's unimodal. The second one, it's a little trickier. We see a big bump in the data right here, but what about this other bump? We look at it and we go, well, compared to the right-hand side, it doesn't really stick up a lot. So we're still going to go with that there's one mode, unimodal. Now if we look at this last one, we can clearly see there's a hump in the data here and a hump in the data here. So there's two clear spots where it sticks out. So this is a bimodal histogram. Alright, so now you should be able to construct a frequency distribution for a qualitative data set. You now know how to construct histograms, and finally you can determine the shape of a distribution from its histogram.